Hello student, welcome to EPG Pathsala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today we are going to discuss about the module Nanowire, Properties and Application under the paper Nanoscience and Technology 2. After completing this module, the student will able to learn what is nanowire. They will also learn the properties of a nanowire like photoluminescence, thermal, doping, etc. They will be able to learn the various application of nanowire in solar cell, FET or LEDs. So nanowire are especially attractive for nanoscience study as well as for nanotechnology application. Nanowire compared to other low dimensional system have two quantum confined directions while still leaving one unconfined direction for electrical conduction. This allowed them to be used in application which requires electrical conduction rather than tunneling transport. Because of their unique density of electronic states, nanowire is the limit of a small diameter and expected to exhibit significantly different optical, electrical and magnetic properties from their bulk 3D crystalline counterparts. Increased surface area, very high density of electronic states and joint density of state near the energy of their von Hoff singularities enhance excitation binding energy, diameter dependence band gap, and increased surface scattering for electron and phonons are just some of the way in which nanowire differ from their corresponding bulk material. Not only nanowires exhibit many properties that are similar to and other that are distinctly different from those of their bulk counterpart, nanowires have the advantages from an application standpoint is that some of the materials parameters critical for certain properties can be independently controlled in nanowire but not in their bulk counterpart. Certain properties can also be enhanced non-linearly in a small dimension nanowire by exploiting the singular aspect of 1D electronic density of state. In this module, we study the interrelationship between the structure and properties of nanowire and their different applications. I want to discuss about nanowire. The development and quality of extremely small electronic circuit are critical to how well future computers and other electronic devices will function. Nanowire are extremely thin nanocrystal threads used in the development of new electronic components like transistors. Part of the challenge of working with nanowires is creating a good transition between these nanowires and an electrical contact to the outside world. Nanowire is a solid rod-like material or structure with diameter of the order of nanometer. Similar to the conventional wires, they are also manufactured from semiconducting metal oxide metals or carbon nanotubes. Due to their size, they exhibit unique thermal, chemical, electronic, optical and mechanical properties which are not found in bulk materials and which have their related field of applications. Nanowire is produced under controlled conditions and can be manufactured via several processes such as vapor deposition, vapor liquid synthesis, and suspension. Nanowire can be metallic, insulating, or semiconducting in nature. It exhibits high flexibility and it's high in strength and uniform morphology. Metallic nanowire exhibits enhanced magnetic coercivity compared to their bulk counterpart. As for thermoelectric properties, metallic nanowire shows high Seebeck coefficient because of enhanced density of electronic states. Thus, it can conduct heat or electricity substantially higher than any bulk material. When it comes to electrical property, the crystalline structure of nanowire increase the electrical properties by many fold. The large surface area of nanoparticles provide motivating catalytic properties of nanowire. Considering optical properties, metallic nanowires shows unique plasma absorption effect on linear properties are also shown by nanowire array. The unique capabilities and features of nanowire hold lot of promise for applications in different fields like optics, electronics, and magnetism. The high aspect ratio, high number of surface atoms, and enhanced surface to volume ratio makes nanowire attractive for sensor application such as nanosensor. They are also used in small electronic circuit, transistor, memory devices, and quantum instruments. Nanowire is also used in producing nanoprobes and nanophotons. Some images of various nanowires has been shown here in figure. The first figure shows the gallium nitride single wire. The second one is the array of zinc oxide nano rod, and the third one is the array of silicon nanowire. So, nanowire is the smallest dimension which can transport charge carrier, electron and hole. A nanowire is a wire of dimension the order of nanometer, which is of the order of 10 power minus 9 meter. Alternatively, nanowires can be defined as a structure that have a lateral size constrained to 10 of nanometer or less and an unconstrained longitudinal size. At this scale, quantum mechanical effects are important. Hence, such wires are also known as quantum wires. Many different types of nanowires exist, including metallic, nickel, platinum, gold, semiconducting, indium phosphide, silicon, gallium nitride, and insulating, silicon oxide, titanium dioxide. Molecular nanowires are composed of repeating molecular unit, either organic or inorganic. Let us discuss the optical properties of nanowire. Optical method provides an easy and sensitive tool for measuring the electronic structure of nanowire. Since optical measurements requires minimal sample preparation, for example, contact are not required, and the measurements are sensitive to quantum effect. Optical spectra of one-dimensional system, such as carbon nanotube, often show intense feature at specific energies near singularities in the joint density of state formed under the strong quantum confinement conditions. A variety of optical techniques has shown that the properties of nanowire are different from those of their bulk counterpart. Although optical properties have been shown to provide an extremely important tool for the characterization of nanowire, the interpretation of these measurements is not always straightforward. The wavelength of light used to probe the sample is usually smaller than wire length but larger than the wire diameter. Hence, the probe light used in an optical measurement cannot be focused solely onto the wire and the substrate on which the wire rests or host material if the wires are embedded in the template are simultaneously probed. For measurements such as photoluminescence, if the substrate does not luminesce or absorb in the frequency range of the measurement, PL directly measures the luminescence of nanowire and the substrate can be ignored. In reflection and transmission measurements, however, even a non-absorbing substrate can modify the measured spectra of nanowire. For example, PL properties of semiconducting nanowire have shown in this figure, from where we can see that PL of the side direction depends in case of nanowire, such for parallel gives PL, and PL is off in case of perpendicular direction. Also, the PL intensity is uniform along the wire length and along perpendicular period cos square alpha dependence. Optical properties, the size dependent PL. Photoluminescence, which is known as PL, or the fluorescence spectroscopy, is a common method to study nanowires. Emission techniques probe the nanowire directly, and the effect of the host material does not have to be considered. This characterization method has been used to study many properties of nanowire, such as the optical gap behavior, oxygen vacancies in Llano nanowire, strain in silicon nanowire, and quantum confinement effect in indium phosphide nanowire. The photoluminescence of indium phosphide nanowire as a function of wire diameter has been shown in the figure, thereby providing direct information of effective band gap. As shown in the figure A, when the wire diameter of an indium phosphide nanowire is decreased so that it becomes smaller than the bulk exciton diameter, which is of 19 nanometer, the quantum confinement effect set in and the band gap is increased. This result is an increase in the PL peak energy because the stronger electron hole Coulombic binding energy within the quantum confined nanowires. As the wire radius gets smaller than the effective Bohr radius for exciton for bulk indium phosphide, PL of indium phosphide nanowires at very low temperature 7K have been shown in figure B. From this figure, we can see that as diameter decreases, again the PL intensity shifted towards higher energy. The motion of the electron in nanowire can be considered similar to a particle confined in an infinite cylinder. By solving the Schrodinger equation for particle in a cylinder, one can get the following expression, such as the wave function psi equal to nz0 alpha R by R sine pi Z by L. And energy shift delta E is H cut square by 2m star alpha by R square plus pi by L square minus psi xh mod E square epsilon x E minus xh psi xh psi xe. From the above expression, we can see that the charge in energy is dependent on the radius and length of the nanowire. Shows the photoluminescence of indium phosphide nanowire as a function of wire diameter, thereby provide direct information on the effective band gap. As the wire diameter of indium phosphide nanowire is decreased so that it becomes smaller than the bulk exciton diameter of 19 nanometer, quantum confinement effect set in and the band gap is increased. This results in the increase in the PL peak energy because the stronger electron hole Coulomb binding energy within the quantum confined nanowire as the wire radius gets smaller than effective Bohr radius for excitation for PL indium phosphide. The thermal properties of nanowire. Experimental measurements of a temperature dependence of thermal conductivity kT of individual suspended nanowire can be carried out to study the dependence of kT on the wire diameter. In this context, measurement made on nanowire down to 22 nanometer in diameter have been shown in the figure. Such measurements are very challenging and are now possible because of technological development in fabricating and using nanometer size thermal scanning probes. The experiments show that the thermal conductivity of a small homogeneous nanowire may be more than one order of magnitude smaller than in the bulk, arising mainly from a strong boundary scattering effect. Phonon confinement effect may eventually become important as still small diameter nanowire. Measurements on mats of nanowire do not generally give reliable results because the contact thermal resistance between the adjacent nanowire tend to be high, which is in part due to the thin surface oxide coating that most nanowire have. These surface oxide coating may also be important for thermal conductivity measurements on individual suspended nanowires because of the relative importance of phonon scattering at the lateral wall of the nanowire. Thermal conductivity is defined equal to K equal to 1 by 3 CV multiplied by V multiplied by L, where CV is the specific heat, V is the velocity of phonons, and L is the mean free path. The most extensive experimental thermal conductivity measurements have been done on silicon nanowire, where the thermal conductivity K measurements has been done on nanowires in diameter ranging from 22 to 115 nanometer. The results shows a large decrease in peak of kT associated with Umklapp processes as the diameter of nanowire decreases, indicating a growing importance of boundary scattering and a corresponding decreasing importance of phonon-phonon scattering. At the smallest wire diameter of 22 nanometer, a linear dependence of K is found experimentally consistent with a linear d-dependence of specific heat for one-dimensional system and a temperature-independent mean free path and velocity of sound. The properties of doped nanowire. Here in this slide, I will discuss the properties, especially the electrical properties of nanowires. One can change the electrical properties of nanowire by doping it with various dopant atoms, such as silicon and boron. Doped nanowire shows p-type behavior and phosphorus doped nanowire shows n-type behavior. The result has been shown in figure A. However, nanowire can also be made metallic by increasing the amount of dopant atom, or in other words, by heavily doping. The result has been shown in figure B. Let us learn the application of nanowire. Perhaps the most obvious use for nanowire is in electronics. Some nanowire are very good conductor or semiconductor, and their minuscule size means that manufacturer could fit millions more transistors on a single microprocessor. As a result, computer speed would increase dramatically. Nanowire may play an important role in the field of quantum computers. Research has been carried out on nanowires out of indium arsenide and attach them to aluminum electrode. As temperature near absolute zero, the aluminum becomes superconductor, meaning it that superconductivity without any resistance. The nanowire also becomes superconductor due to the proximity effect. The researcher could control the superconductivity of nanowire by running various voltages through the substance under the wire. A new design of nanowire graphene based solar cell have been shown in the figure. This new design consists of layer of graphene, which is a transparent cathode, a conducting polymer, maintained integrity, and ZNO nanowire layer as electron transport. Lead selenide quantum dots, hole transport, AU layer as a anode. The efficiency of this device approaches ITO based solar cell, which is having 4.2. Conventional efficiency is around 5.1 for ITO, and also cheaper to produce such solar cell with respect to current silicon and ITO based solar cell. I want to discuss the applications of nanowire. Nanowire can be used for making field effect transistors, FET. Transistors are used widely as fundamental building elements in today's electronic circuit. As predicted by Moore's law, the dimension of transistor is shrinking smaller and smaller into nanoscale. One of the key challenges of building future nanoscale transistor is ensuring good gate control over the channel. Due to the high aspect ratio, if the gate dielectric is wrapped around the nanowire channel, we can get good control of channel electrostatic potential, thereby turning the transistor on and off effectively. Due to the unique one-dimensional structure with remarkable optical properties, the nanowire also opens new opportunities for realizing high-efficiency photovoltaic devices. Compared with its bulk counterpart, the nanowire solar cells are less sensitive to impurities, due to bulk recombination, and thus silicon vapor with lower purity can be used to achieve acceptable efficiency, leading to a reduction of material consumption. To create active electronic element, the first key step is to chemically dope a semiconductor nanowire. This has already been done to individual nanowire to create p-type or n-type semiconductors. Nanowire based FET has following advantages. Number 1. There are several nanowires of different properties, so these could be used as channel for getting various properties. Nanowires show very high mobility, which is desired as channel material in FET. Bottom-up synthesis of nanowire provides easy fabrication of FETs. Nanowire's FET has following challenges too. The first one is the integration of nanowire into circuit is a little bit crucial. Controlled growth of having uniform diameter and length is also very tough, and controlling dopant atom is also not easy. Now let us discuss the application of nanowire as LEDs. Nanowire could be potentially used for making light emitting diode, which is called LEDs. LEDs made from nanowires will be less energy and provide better light. For an example, here I have taken gallium nitride nanowires. The gallium nitride nanowires only be a few tenths of the micrometer in diameter, but they promise a very wide range of application, from light emitting diode and diode laser to ultra small resonators, chemical sensor, and highly sensitive atomic probe tip. In the 2 decades since gallium nitride was first employed in a commercially viable LEDs, accompanying in a stunning future for low power lighting and high power transistors. Gallium nitride emits light when holes and electrons recombined at a junction created by doping the crystal to create p-type and n-type regions. These layers are formed by a variety of deposition methods, typically on a sapphire or silicon carbide substrate. Conventional methods produce crystal with relatively high defect densities. Unfortunately, defect in the lattice limit light emission, introduce signal noise, and lead to early device failure. Among other advantages, flawless crystal produce more light. Now, for the first time, the electroluminescence from a single gallium nitride nanowire LED is sufficiently bright that we can measure its spectrum and track the spectrum with drive current to see evidence of heating. Here we have compared LEDs of nanowire in comparison to the conventional lighting source. The efficient, less heat, low power consumption, long life, it is cheap, no mercury is used. How nanowires help? This we can see here. Because of the various geometry of PN junction available, we can have those geometry like coaxial wire, thin film wire combination, crossed wire junction array, unique carrier transport properties, natural waveguide cavities, improve extraction efficiency of light, high area of improved conductivity, and many more. So this way, the nanowire is going to be used in future for many applications which we have discussed. So student, let us now summarize what we have learned in this module. We have seen that this nanowire have the diameter from 1 to 100 nanometer. Length will be micron in size. Their properties are like directional dependent PL, which is parallel in on position, and at perpendicular direction it is off position. Size and temperature dependent PL has been also studied. The thermal conductivity decreases with decrease in diameter. Doping can lead to make it p-type or n-type. There is a many application in solar cell, in FET or LED has been discussed. So this is all about this module. Thank you very much.